Hey everybody, John here. We're going to move on to polynomial functions of higher degree now. And so all of these functions look the same. They start with the highest, if they're in simplified form, they start with the highest degree term. So here's a term. Terms are separated by addition or subtraction. These could be negatives as well, or the coefficients could be negative. And basically, so a quadratic starts with the highest degree term, which is this x squared term, and then moves down to an x term, and then eventually down to the constant term, which is here. A higher order polynomial would just have more terms in front. So again, we don't have to necessarily have an x cubed term. So here we have an x to the fourth, we have an x squared, and just to, these could be plus or minus, it doesn't matter. So n, though, has to be a positive integer, which means it has to be a whole number value. And the leading term or the leading coefficient is the coefficient or term that has the highest degree. It's not necessarily the one that comes first, it's the one with the highest number exponent. And again, no fractions for exponents, no decimals for exponents, no negative exponents, which means all variables should be in the numerator. This is what makes a polynomial function of degree n. So let's just practice looking at each polynomial function. We're going to find its degree. We're going to find the leading term and the leading coefficient. Because the leading term and the leading coefficient and the degree are the most important things when you're trying to graph one of these functions. It's important to know if it's an even or an odd degree polynomial. It's important to know what the leading coefficient looks like, and that's going to be found in the leading term. So in this first one, the degree is going to be 4. It's a fourth degree polynomial. It has degree 4 because that's the largest exponent. And since the largest exponent is attached to this variable, this becomes the leading term. So the leading term is 5x to the fourth. The leading coefficient is just the number that comes in front of the x to the fourth variable. So pause the video and see if you can find the degree, leading term, and leading coefficient for this second function. All right, so the degree is the highest exponent. So in this case, this is a third degree polynomial. Some of these have special names too. This is a cubic function, okay? The one before it was a quartic. It's not important that you know those terms. It's just they're out there in case you're interested. The leading term is the whole thing that has that highest degree exponent in it. So that leading term is going to be 7x cubed. The leading coefficient is going to be 5, or not 5. It's going to be 7. Okay. So if we had a function where it was 1 minus 3x to the fifth plus 7x squared minus 9x to the ninth, even though this isn't in order like it normally would be, we should still be able to find the degree, the leading term, and the leading coefficient. In this case, the degree is 9. The leading term is negative 9x to the ninth, and the leading coefficient is negative 9. So this is that term, and this is the leading coefficient. The negative has to go along with it. Okay, so even though it's not the first one there, it is the leading term. So the reason we care about the leading term or the degree is because when we have a single term polynomial called a power function, this is what we're going to refer to when we're graphing. The power function of each polynomial that has a certain degree is going to look similar. And depending on the end behavior especially is going to look similar. So we're going to look to the power function, which is a simplified version. It's very simple, very similar to the parent function, like we talked about in transformations. So we're looking to the power function for end behavior and overall general shape. And then from there we can make other, we can figure some other stuff out using other tools, which we will go through in the subsequent videos, okay? But basic shape is really important here. So the power function, if you have an even degree, we already know one even degree polynomial, that's a quadratic, okay? And the basic shape of a quadratic looks like this when a is positive, and it looks like this when a is negative. Now, basic shape. Does that mean there can't be some other stuff going on here? No, of course there can be other things going on, but the basic shape is to start high, end high, or to start low, end low. That is my basic shape. And the end behavior is exactly what I just described. But the way that we write this in math is we say as x goes to negative infinity. So as we are as far left on the graph as possible, when I look for my graph, is it going to be above me or is it going to be below me? Is it going to be at positive infinity or negative infinity? Well, for a being positive here, if I'm walking along this graph, and I have to look up to find the graph because the graph is way up at positive infinity. So as x goes to negative infinity, f of x goes to positive infinity. And you don't have to write the positive. If you want to really drive the point home, you can say that. Oops, that's an 8. Okay. And as x goes to positive infinity, meaning I'm going to the right on the graph, is my graph going to be above me or below me? It's going to be above again because it starts high, it ends high. So this is starting and ending, and this is high. Okay? And that's for, this is for a is greater than 0 right here. If a is less than 0, I'm going to start, so as x goes to negative infinity, I'm on the left, I'm starting, I'm going to start low, which is negative infinity, and I'm going to end all the way to the right on my graph. I'm going to end low. That is what even degree polynomials basically look like. And they all look this way at the very ends of the graph. And when I say ends, I mean all the way to the left and all the way to the right, as far as you can think of in your brain. Okay? So this is the end behavior for positive leading coefficients, and this is the end behavior for negative leading coefficients. But the basic shape is that quadratic parabolic shape. And I mean basic. If you zoomed out so far that you couldn't see these squiggles here in the middle, it would still look quadratic at the end. If you, and you can try this on your calculator if you really want. Put in something that looks very much not like a quadratic, but then zoom out really far. It's going to look like this. If you zoom out a lot on your calculator, it's going to look like that. All right, so now what if we have an odd degree? Well, same idea. The most basic odd degree polynomial we know of is a line. And a line with a positive slope starts low and ends high. But for our purposes, let's think of this as a cubic function. And it starts low and it ends high. Okay, something like that. And if the leading coefficient is negative, so if your slope was negative, it would start high and it would go down from there. It would end low. And the way that we write this using math is we start as x goes to negative infinity, f of x is going to negative infinity. And as x goes to positive infinity, as we go as far right on the graph as we can think of, my graph is also going up. Okay? But if my leading coefficient, which in the case of lines is the slope, we start, meaning as far left on the graph as we can think of, we start high, so we start at positive infinity, and we end low, that's negative infinity. Okay, so starting is all the way left on the graph, ending is all the way right. High is up, low is down. High is positive infinity, low is negative infinity. Okay, this is what we talk about. This is what we mean when we talk about end behavior, and we use this notation that we have here. Again, pause and rewind if you need to go through that again. You might also want to read a little bit in your book about it, or do the problems associated with this in the study plan that goes along with the problem set.